Hello everyone, we are students of Mondragon Unibertsitatea and we are presenting our project to the Simulink Student Challenge 2012. Our work consists on modeling, control and 3D animation of a quadcopter like an air drone. For the development of our project, we have used Matlab Simulink and the 3D animation toolbox of Simulink.
But what is a quadcopter?
A quadcopter is an aerial vehicle used for transportation, ground recognition or just for entertainment. It has 4 rotors placed horizontally, which allows a more stable performance.
The geometric position of the 4 rotors allow us to control 4 main movements in the quadrotor. The first one is throttle, that allow us to control the altitude of the helicopter, and the other one are roll, pitch and yaw, the Euler angles, that allow us to control the angle of the quadcopter in every direction.
So here we can see the Simulink model of the whole system. First the quadcopter model, then the control algorithms to control the model, then the high-level controller, and all the plots needed for the system. Let's see the quadcopter model. We have used some color notation for the variables. In magenta we can see the local variables of the system. Then in red the global variables go into the plots, and in orange and in cyan the inputs and the outputs of the system. Let's see how the kinematic and dynamic model works. In this block the Coriolis centripetal, gravitational and gyroscopic effects has been taken into account, among with the friction of the air. Here we can see the model of the motors, considering also the inverter feeding each motor. There is also the load torque generated in the blades and the motor encoder. And here in this block there is the conversion between the speeds in the motors and the force applied in the model.
So now let's see how the control works. Here we can see the entire block diagram. First of all, we have both torque and speed loops controlling the motors, and then a speed loop attacking the inverted model of the entire quadcopter, which practically annihilates the dynamics of the model, and finally we have a position loop controlling the instantaneous position of the quadrotor. Every loop has been adjusted using SISO tool. Back to the model, we have the motor loops consisting of 4 controllers for the 4 motors, all of them implementing the torque and speed loops mentioned. Then we have the PI inverse control block. There they can be found the inverse model of each degree of freedom, roll, pitch and yaw, and both position and speed control loops. Apart from these blocks, there is another block to convert the forces into the motor speed references, where it can be found a block converting the throttle, roll, pitch and yaw forces into motor speeds, and a Matlab embedded function block used for considering some limitations derived from the imposition of positive angular speeds on every motor. Finally, the complete root locus of the entire system can be seen. Apart from all these low-level controllers, a block to include any high-level controller that can manage the genetic trajectories has been constructed.
And finally, in this subsystem we can see all the plots. For a proper understanding of all the data, a 3D animation of the quadcopter has been built. Now we can see from a moving camera how the quadcopter continues the reference really well, being the reference the blue line and the position the red one. Also, a part has been simulated, firstly to see that the acceleration, speed and position have normal values. Secondly, to appreciate better any strange movement in the results analysis. Having more than one camera is helpful because maybe with one camera you might not notice the full range of movements of the quadcopter, and having some objective cameras and others objective allow the user to observe the full kinematic of the movements in any case. Finally, the 4 basic movements which the quadcopter can do are shown: throttle, roll, pitch, and finally, yaw.
The main goals of this project have been to model, control, and animation of a quadcopter with Simulink Animation 3D. The model build is highly realistic, taking into account all the dynamics effects, even the gyroscopic ones, simulating every motor and inversion and being the parameter values measured from a real quadcopter. Matlab Simulink has been essential for implementing all the project, especially the 3D animation toolbox, converting the result of the simulation from some plots to highly understandable animation. The interpretation of the movement of the helicopters is much more intuitive than before, as a 6 degree of freedom system is not trivial to analyze. The simulation build is very useful to design high-level controller. Using the entire model as a black box, the user can see a realistic output of the control designed. Finally, the Simulink model for the whole system is really intuitive, and it is well organized, so its interpretation is really easy even for the first view of the system. We thank you very much for your attention.